Hello and welcome to the Data Engineering Podcast, the show about modern data management. What are the pieces of advice that you wish you had received early in your career of data engineering? If you hand a book to a new data engineer, what wisdom would you add to it? I'm working with O'Reilly on a project to collect the 97 things that every data engineer should know, and I need your help. Go to dataengineeringpodcast.com/97things to add your voice and share your hard-earned expertise. And when you're ready to build your next pipeline or want to test out the projects you hear about on the show, you'll need somewhere to deploy it, so check out our friends over at Linode. With their managed Kubernetes platform, it's now even easier to deploy and scale your workflows or try out the latest Helm charts from tools like Pulsar, Pachyderm, and Dagster. With simple pricing, fast networking, object storage, and worldwide data centers, you've got everything you need to run a bulletproof data platform. Go to dataengineeringpodcast.com/Linode, that's Linode, today and get a $60 credit to try out a Kubernetes cluster of your own. And don't forget to thank them for their continued support of this show. You listen to this show to learn and stay up to date with what's happening in databases, streaming platforms, big data, and everything else you need to know about modern data management. For more opportunities to stay up to date, gain new skills, and learn from your peers, there are a growing number of virtual events that you can attend from the comfort and safety of your home. Go to dataengineeringpodcast.com/conferences to check out the upcoming events being offered by our partners and get registered today. Your host is Tobias Macy, and today I'm interviewing Dr. Denise Gosnell and Dr. Matthias Broecheler about the recently published Practitioner's Guide to Graph Data. So, Denise, can you start by introducing yourself?
Yeah, thank you so much. It's great to be here. As you mentioned, my name is Denise Gosnell. I run the data ops organization here at DataStax and had the honor to co-write this book with Matthias. So thank you so much for having us here.
And Matthias, how about yourself?
Hello. Yeah, thanks for having us here. My name is Matthias. I also work at DataStax. And my current role is in product strategy. So I work with the product team to identify strategic areas of investment and making sure that our products meet the market and customer needs.
And Denise, do you remember how you first got involved in the area of data management?
I do, and there's potentially two different main areas. The first of which was a complete accident for getting involved in graph data, and then the second of which was starting to build with graph technologies. So I got involved in graph theory and graph data as a part of my master's degree. It was purely an accident because I was locked out of other courses and I didn't know what graph theory was. But during that semester and studying with Dr. Teresa Haynes, I found a passion of working with connected data that has led me to getting to meet and talk with you today. And as a part of one of my jobs as a data scientist and data engineer, I was building the world's health graph and mapping out all of the healthcare transactions within the United States. And we were using open source technologies back in 2014 for that, which led me to using Titan and meeting Matthias as well as part of my collaboration with building on Titan. So both of those two events are how I got involved in data management and specifically with graph technologies.
And Matthias, do you remember how you first got involved with data management?
It actually goes a long, long time back. I read a biography of Goethe, who is a German poet and also polymath. And one of the things that just kind of stuck with me was that at least the author claimed that Goethe was the last human on Earth who had all the world's knowledge in his library and was able to sort of comprehend everything there was to know at his time. And that just really fascinated me to think about having the ability to tap into anything that is knowable sort of within arm's reach, and kind of never let go of me. So obviously part of trying to make that happen was looking into data and information management. And I got involved in semantic web research and sort of that was my first foray into graph data, semantically structured data and RDF and the linked semantic web and all these initiatives. Did a lot of research there and got really interested in how do you make this technology scale so you can really truly represent all the world's knowledge, which in the last couple hundred years has obviously expanded quite a bit. And then got interested in doing my PhD research at the University of Maryland in graph database systems, and in particular scalable graph database systems, the result of which then culminated in the open source project Titan that Denise just talked about. Started a company around that called Aurelius with my co-founder Marco Rodriguez, and we ultimately got acquired by DataStax, which is where I am now, to bring graph technology to a wider market. So it's been a long journey over the last 20 some years, from sort of this vague idea of wouldn't it be fun if we could capture somehow all the world's knowledge, all the world's information, all the world's data in a format that is representative of how humans think about data, to making the technology happen.
And moving into the topic at hand today is the book that you both co-wrote on the Practitioner's Guide to Graph Data. So I'm wondering if you can just describe a bit about what your goals were in that book and your motivation for writing it.
Yeah, that's a great question. And so I think there are maybe two motivations that I would like to call out. And Matthias, maybe you might have another perspective as well. But those two motivations were to communicate common patterns, but then also to kind of bring together both worlds that I had been observing within the graph space. So just a little bit of each of those. As I had started building with graph technology, and then after the acquisition of Aurelius to DataStax, came over here to the team to be a part of building some of the world's largest graph applications. We started discovering that there's a common set of patterns that companies and people were using for deploying and using graph technology in production applications. And what we wanted to do was to essentially tell stories about what those patterns were in a tangible way to teach them to others. Just like you've seen relational databases kind of converge on common approaches to problems, we're starting to see that in the graph space as well. So that was really one of the technical cornerstones of what we wanted to write the book about. And then second, when you kind of were hearing Matthias and I introduce each other, you can kind of see that we have two different approaches or two perspectives maybe to working with graph data. And I thought that it would be an incredible partnership to bring together for just kind of bringing the data-oriented approach, but then also the long history that Matthias has from building these systems from within data management solutions and technologies, bring them together to kind of teach the world about how this works end to end. So those are kind of the two primary cornerstones that I know Matthias and I have spent a lot of time talking about on why we wanted to write this book together. But Matthias, I'm curious if you have anything else that you'd like to add or another perspective to that.
I think you captured it beautifully. I think there's a wide need right now in terms of learning more about these technologies. And one of the things that Denise has done in many years of her career is work very closely with customers on these problems. So she has a very practical approach to working with graph data, which is one of the reasons we picked that title for the book. And combining that with a sort of foundational understanding of graph technology, we go into the details of the terminology and spend a good amount of time in the book to talk about graph thinking. So the way that you approach graph problem is fundamentally different from how you approach sort of tabular structured problems that we're most familiar with. So there's a huge need to kind of explain how to use graph technology, not just from a sort of nuts and bolts perspective, but also from a zooming out and understanding what problems you should be looking for before you apply graph technologies to them.
And I thought it was interesting in looking through the book a little bit that you called out the fact that the past 2 decades have in large part been the era of NoSQL, with trying to scale horizontally to address the projects and applications that are using growing volumes of data, needing to be able to process those scalably, and that the previous 2 decades were dedicated to relational databases as the overall space of digital data management grew and matured. And you're saying that the current decade that's starting now is going to be the realm of graph data and this growth in graph-oriented thinking. I'm wondering what you see as the driving force behind that growing popularity and the need for graph technologies, and how that's going to shape the future trends in technology.
I think the big trend that we see just going back after the last era of data management, the scaling out, we saw just so much data being captured and companies and individuals trying to catch up with that data, being able to put it somewhere and put it to use. And I think now that we have sort of kind of wrapped our heads around, like, how do we manage this much data located all over the world? I think the next frontier in data management is, how do we get the maximum amount of value out of this data, right? I think of it as kind of like, if you imagine like you open a fire hose, like the first problem you have is, what do we do with all the water? Like, where do we put the water? And then the next problem is, how do we put this water to good use? And graph technology really zooms in on the latter problem of understanding how the relationships in the data make the data more valuable. They amplify value in the data. The more you can connect data, the more valuable it becomes. And that, I think, is a fundamental insight that more and more companies and individuals are arriving at. And we're currently just at the very frontier of that. But I believe that the next decade or so, we'll see much more of that, where these people sit down and say, okay, we have this data now. How can we get the maximum amount of value out of it to drive better value propositions, to build better products, to have better customer experiences, whatever it is that your organization is optimizing for, by being able to look at the data as interconnected pieces that enrich each other, you are in a position to build better experiences. And you can already see some companies doing that and outcompeting other companies. And through that pressure, we will see more and more technology teams being sort of led to the graph table. And that's, I think, is sort of the reason for that shift towards graph technologies, which obviously does not mean that any of the older technologies are being invalidated, right? Like the rise of NoSQL did not diminish SQL or the relational model. It enriches it. And we similarly think that graph is sort of the next layer on top of the data management cake of being able to put all of this data together and make it more valuable.
And on that point, too, there's the interesting question of the way that graph information is manifested, where there are plugins for relational systems or data modeling techniques for being able to embed a graph into a relational model using things like RDF triples or associative data structures. But then there are also database technologies that are specifically built for being able to store and analyze graph structures. And I'm wondering what your thoughts are on the overall trade-offs of when to use which implementation, and your thoughts on the use of graph databases as the primary data store or as something complementary to a different data store that acts as the canonical source of truth.
Yeah, that's a deep that's a deep and very multifaceted question. So I think I want to start with the first piece when you were kind of talking about like when to use graph technology. If I heard you correctly, is that right?
Yes.
Okay. Yeah. I like when I think people ask us this all the time. This is probably one of the most popular questions that Matthias and I have the opportunity to coach and talk to teams about. And it really starts at the beginning. We like to think about or coach people through thinking whether or not the problem they're describing needs graph data. And what we really mean by that is whether or not the relationships or the links or the connections within or across your data helps provide more insight or helps provide more understanding for the problem you're trying to solve. If you're thinking about those questions with your problem and you're screaming yes, like absolutely, that's a telltale sign that you do need graph technology. But more often than not, when we have those conversations, people are thinking, well, I really don't know. I don't know if my problem needs connected data. And usually we will take the problem that we're working with and try and break it down a little bit further into a smaller question and really begin to just digging in a little further, where you're trying to find at any point, do you need connected data across your systems to answer this question? Because once you do get a true yes, that's really when you're moving into the realm of graph thinking or needing graph technology. And from there, potentially oversimplifying, but from there, Matthias and I really, we commonly see and talk about there being two approaches, whether or not you're really looking at needing a graph database or you're really talking about graph algorithms. So I'm going to talk about the latter first. So when you know that you need relationships in your data, the next step that you really want to do with it is to put it into a graph structure and to analyze it. Maybe you need to understand the betweenness centrality across your whole graph, or you want to understand page rank for your graph. When you're thinking about these global analytics or the global understanding of the topology of your data, you're really thinking about graph algorithms and wanting to apply the very famous and common set of approaches for studying the connections and the structure and the shape of your graph data. And when you're working within graph algorithms, you probably just need some type of report, or you need to kind of be working more traditionally within the data science or machine learning workflow, more R&D style, right? Like you're just trying to understand this new structure and how it applies to your problem. Once you've iterated on that and you have found that valuable answer that you maybe need to serve in a production application, that's when graph databases or storing and querying specific relationships or links between entities becomes very valuable to do in a production application. And that's when you'll want to use a graph database. And how we think about this very commonly, just to kind of give you a very specific example, is to think about, let's just go with LinkedIn as an example. When you start with LinkedIn and you hit that search bar, you're probably typing someone's name. And the first problem from a tech perspective that you're experiencing is search and doing character completion. And that type of search is just a semantic way to match what you're typing to a list of names. And that's not a graph problem. That's a search and a character edit distance problem that you probably solve with like Elasticsearch or some type of tech like that. On the other hand, though, once you look at your search results, I guarantee you that they're probably listed in order by connection. And you can imagine on LinkedIn, you see those badges of first connection, second connection, third connection. You can kind of imagine those results. That is exactly explaining and helping you understand the professional network according to how you fit in, according to your connection to that person. And serving that badge is a beautiful example of how you use graph algorithms and storing and querying them in a real-time production application together at the same time to serve one feature that we all use all the time on LinkedIn. Because, doing global pathfinding to determine the total number of connections between you and anybody else you could search for on LinkedIn, that's not something you're going to do real time on query when you're searching for somebody. That's going to be done as a graph algorithm, and they're going to store those results in a database to query when you search for somebody. So when you kind of think through end to end of how you search for a person on LinkedIn and how you create that personal story about how you know them through mutual connections or how closely connected you are, that entire journey it kind of steps through whether or not your problem needs graph data, whether or not you're using graph algorithms, and then how to maybe store and query a graph-specific feature in the end application. So that's how I like to think about that question. It's a great one.
And in understanding the fundamental principles of the graph technologies and the algorithms that are useful in that context and the different technologies that are necessary for being able to power those use cases, what are the core concepts that data teams and data engineers need to be familiar with and be able to understand to employ those technologies and those algorithms effectively?
That's a great question. It's another one of those where I could talk for like 30 minutes straight because there's quite a lot of nuance to it depending on the use case you're targeting. I think the initial phase is the most critical one, where you really dive into the problem that you're trying to solve, the particular use case you're looking at, the particular application, whatever it is that you're building, and really break apart what part of this problem is generally a graph problem, meaning a problem where you want to analyze relationships, where you want to use the connectedness of the data to infer something or to enrich the use case that you're trying to solve. And once you have zoomed in on what those components are, to then break it down, and like Denise was talking about, sort of the analytics side, where you focus more on sort of global optimization, global type of graph problems versus real-time graph problems like pathfinding. And Denise gave the example of PageRank for a global one, to kind of drill down into those pieces. But also at the same time, and this is where it gets a little more complicated and nuanced, is keeping in mind what the overall problem is that you're trying to solve, to keep that in context. And what I mean by that is that oftentimes when you look at graphs, for instance, in a streaming context, right? So you have like individual events coming in that over time build a ginormous graph that you're trying to analyze. An example being cybersecurity type use cases. Then you want to make sure that the overall technology pipeline that you're building is sort of attuned towards the streaming nature of your particular use case, and you want to find an underlying technology that can handle those kinds of high velocity streaming use cases and build a graph over time that you can analyze in real time to then do threat analysis, for instance. And that's, there's a lot of nuance in that. There's very many technologies out there right now. And one of the really exciting things about the graph space is that it's unsettled right now. Like we're still in the sort of experimentation phase where we're trying to figure out which products work well for which use cases. So if you're building a knowledge graph, for instance, you're likely making very different technology choices than if you're trying to build a cybersecurity solution that looks at, networks of data and packages being sent forth, which is very different than if you're trying to do supply chain optimization and, supply chain type analysis to have a better commerce infrastructure. So in those different use cases, the real key is to understand which part is the graph problem uniquely and how is that embedded in the larger problem, to make sure you make system choices and technology choices that are harmonious within the overall architecture that you're building. And there's different products out there. There's like, for instance, at DataStax, we have a multi-model graph database, which allows you to store data in multiple forms, one of which is graph, which is really useful for instance, event streaming use cases or other use cases where you also need to look at the data in tabular form or retrieve it differently. Then there are standalone graph technologies that really focus on just the graph component of a problem, which can be a great solution for, let's say, a knowledge graph. And so it is a bit nuanced, unfortunately. And as we learn more about the space and more about how people solve problems, I think we get a clearer and clearer picture for how to solve them. But I think coming back to the most fundamental thing that you need to know is at the very beginning to take the time to really break down the problem and understand which part is generally graph and which part maybe does not need graph technologies. Because that's where we see a lot of people kind of get through that phase a little too quickly and maybe then look at parts of the problem that may not require graph technologies or miss parts of the problem that should actually be solved with graph technologies. And then everything else beyond that point becomes a lot harder to do because it doesn't quite line up with the technology choices you're making in the subsequent steps.
There was a similar evolution that I saw when we were going through some of the NoSQL phase of things where people were just starting to throw NoSQL at everything because they said, oh, I need to be able to scale even if they're just starting off with a single server and not understanding what the trade-offs are in terms of the data model and how to think about the problem in a document versus a relational structure. And so it sounds like there's a similar pain point happening with graph technologies where they see graph as this solution for everything. And so they say, oh, we'll just put everything in the graph and not knowing that, well, at some point we want to be able to query this in a relational model instead of being relationship oriented, or we want to be able to collect everything as a single document view. And so given that, what are some of the data modeling principles that are useful as you are going through that solution of defining the domain that you're working in and figuring out where the graph fits, what the actual components of that graph are going to be, and when you might want to push some of those concepts into a different type of technology and maybe in a relational or a document-oriented structure?
Yeah, that's I think that's a really great question. So when you think about some of the common data modeling principles for graph structured data, there's kind of at the beginning, towards the end of your question there, you were starting to highlight the way I see the world as a data practitioner and whether or not I choose graph technology, but then there's actual data modeling principles once you're in graph technology. So as just a general practitioner who likes to build applications, I think in terms of shapes of data. And I'm always looking at the problem, trying to dissect it of if it's, if it really is just a table, or if we're talking about like a JSON or a document shape for, just kind of really understanding the shapes of information that we're sharing across our APIs in our app. And so from that perspective, that's how I begin to, start to educate my teams and the people we work with on how to make smart choices about what components are in your technology stack, just kind of by understanding the shape of data. And the important feature that you hear us talk about, and that really, really comes from what we're hearing Matthias say, is that the most important piece of needing graph technology and graph data comes from when relationships or links across your data are the primary data modeling element of your problem. And whenever relationships are more important, that's when you need to be modeling with graph technology. And so from there, some of the common data modeling decisions to highlight, kind of really far into the weeds, you can think about whether or not between any two pieces of information, you want there to be exactly one relationship or there more than one relationship. That's a really, really common item to think about. So we talk about this in context of banking customers. And, a common data modeling decision is to say whether or not a person can only own or have one relationship with their bank account, or if they can have, multiple relationships with their bank account. So to think about this, you're a person and you own a bank account. So that's kind of like one way to have a relationship between a person and another entity, namely an account. But you probably can have many roles for how you own that account. So you can be the primary owner, you can be the administrator, you can have, different types of permissions. And in that aspect, when you're thinking about wanting to have multiple roles in your account, you're really thinking about multiple relationships between that person and that account. And so the nuance or the difference between what I just described is probably one of the first and most fundamental types of data modeling decisions that you're going to come to when you are working with graph data. And Matthias mentioned a few times just a moment ago about working with event streams and time series data. And if the role example between people and accounts seems a little abstract, you can also think about different sensors that send communication over time to other sensors. And so those are going to be different vertices or different endpoints in a graph that communicate with other endpoints over time. This could be cell phones texting and calling other cell phones as another example. And you're going to have multiple relationships between any two individual endpoints. And having a way to model that in your database, to model time on that edge, because the communication between those two pieces is the most important piece of that problem. Knowing how to use different properties in your graph data to model the quantity of relationships between two pieces of information is extremely important, and probably one of the first data modeling items that we run into when we are working with customers and their graph data models. I'm curious, Matthias, if you had other common data modeling piece of advice that you would like to mention beyond just the multiplicity of an edge between two vertices.
I would say, I mean, we can obviously go much more into the details, but I think that would be harder to follow like verbally. I think we spend a good amount of time in the book to really nail down like what are some of the things that you need to know on a use case by use case basis that really inform graph data modeling. Going back, I think, to the point that Denise made about relationships being a central component. I think that's really, really critical, because that's very different from other types of data modeling and other ways of looking at the world, where you kind of think much more in terms of entity to table mapping, and entities are sort of the central component and relationships are somewhat secondary, and they're used to kind of structure your domain, but not really meant to be used for enriching the data as you query it, as you build use cases around it. And so I think that is the biggest shift in thinking as it comes to graph data modeling and schema design, is how do you design the edges to make sense of your domain? We try in the book, we try to use some analogies in terms of language, something that came about in the semantic web, where you sort of look at how you would talk about your domain of interest in nouns and verbs, and use those to then structure them as vertex labels and edge labels respectively. And so there's a number of techniques and sort of rough cut approximations that help you to sort of get started in that area. But I would say that really is one thing that I personally had to learn, and I've seen everybody who has been using graph technology learn over time, is to really embrace the notion of edges, of connectivity, and to lean on that heavily in solving problems. And that, needs to be reflected in the schema design. And getting there is initially a non-trivial problem, because we just don't have a lot of practice in it. Most people who have gone through a computer science degree don't talk much about it. And so that's really something you need to learn in the beginning to kind of feel comfortable in that space.
Today's episode of the Data Engineering Podcast is sponsored by Datadog, a SaaS-based monitoring and analytics platform for cloud-scale infrastructure, applications, logs, and more. Datadog uses machine learning-based algorithms to detect errors and anomalies across your entire stack, which reduces the time it takes to detect and address outages and helps promote collaboration between data engineering, operations, and the rest of the company. Go to dataengineeringpodcast.com/Datadog today to start your free 14-day trial. And if you start a trial and install Datadog's agent, they'll send you a free t-shirt. And in terms of the actual data types and data structures that you're working with on these edges and vertices, are there any commonalities between the different data storage engines as far as what the structure looks like? Where are you storing a JSON document or a set of tuples as you would in a relational database, or key values for different elements? And is there generally some sort of variance in terms of the type of information that you can store on the edges versus the vertices?
Yeah, I would say that in the graph world, there is some convergence happening around the property graph data model as sort of the underlying principled approach to schema and graph data structure. There's still nuances and some variations in what that means specifically, and vendors sort of differ in how they interpret that. But the general gist of it, like if you look across the various implementations, you can say that there's basically two approaches to graph data. One based in the semantic web with RDF and Sparkle, and the other in the property graph model, and then using a query language suitable to the property graph model like Gremlin, Cypher, or some other variants that are currently in discussion and in design.
And then going into the types of challenges that data engineering teams and other people working with the technologies and the applications might be facing, what are some of those challenges that you see when people try to bring those graph applications into production and start to try and deal with some of the scaling pressures that they might have as they bring more people on board and bring it to more different applications?
Yeah, that's a great question. And first, when you were asking that, I was kind of thinking about I would say the three most common challenges that we've worked through. Just deal with teaching people about the new processing paradigms that come with querying deeply connected data instead of just querying directly from tables. And we talk about those kind of in three terms. We talk about them from the perspective of branching factor, supernodes, and then also just from the perspective of more analytic style queries. And when we mention branching factor, we're talking about just the total number of edges that you process from a vertex as you walk deeper through your graph. So if, just to make math easy, if every vertex has two edges connected to it and you keep walking out, that's going to be an exponential growth on the number of pieces of data that you're processing in your traversal. So the first thing that teams very commonly run into is the problem with branching factor and the overall processing time for any individual query. And they're always left thinking, well, why is this taking so long? And, by the very nature of working with connected data and being able to very expressively explore it with a graph query language, you end up asking for much more data from your application than you originally thought. And the first place to look is typically because of branching factor. We commonly advise teams to be only querying, say, the most recent edge, if that makes sense in their application. So that's a very common technique that people implement by putting time on edges and only going for most recent elements, just as a specific example. But that's the first place that they run into issues. The second place is with the idea of supernodes. And supernodes have both constraints in memory and on disk. You're going to hit the constraints in memory a lot faster than you're going to hit your constraints on disk. And a supernode here is just talking about that vertex in your graph where almost everything points to it, because most natural graphs have a few number of vertices that are highly connected, and the number of edges pointing in or out of that vertex is disproportionately way, way larger than most other vertices, which have only a few connections. So, that vertex in your graph that has almost everything pointing to it is called a supernode. And I think the Twitter example is when they were setting up counters in Cassandra, they discovered that Ashton Kutcher actually was the supernode of Twitter, because they were trying to implement counters and to track the first person to get to 1 million followers. And actually that was the profile that was having issues with implementing that in Cassandra. So when you just think about someone who has as many followers as the celebrities on Twitter, that's what a supernode is. And so when you're walking through those types of vertices in your graph traversal, it's just going to require a lot of memory in order to process millions of edges as soon as you run into a highly connected vertex. So typically we have some recommendations on what to do there, like only walking through a subselection of the edges, or only walking into supernodes, not out of them. And there's a ton of examples that we have in our book on how to get around them. So we'd love to have conversations about that offline. And the third item that I was alluding to is just the balance of running a deep algorithm on request in your application versus storing that analytic to be retrieved. And a good example here is how companies are likely serving up that recommendation window. And we talk about this in the context of movies, because collaborative filtering and doing recommendations for the next movie to watch is a really, really popular feature to put into your application. And to walk from you through the movies you've watched, every person who's watched those movies, and then every other movie to recommend, that's hitting supernodes and branching factor along the way. So very common, teams will set up offline processes to run in parallel offline and learn the recommendations, but store them with what we call shortcut edges, so that you only are walking maybe in a star graph in your actual production application to minimize the SLA for getting that contextualized recommendation. So those three, branching factor, supernodes, and then applying shortcut edges, are our three recommendations for where people commonly get tripped up when they're first writing graph queries and using graph databases.
So the things that Denise mentioned are sort of the very practical things that as a graph practitioner you need to be aware of, and you need to make sure you design around or understand how they will impact your implementation. Then there's also like where my head went in the beginning when you asked the question is like, for in particular people who are relatively new to graph technology, there's an element to sort of kind of to the personal sort of hype cycle of graph that we've seen a lot of people go through, where initially you're new to graph and you're learning it, and then as you learn more about graph, you get to the point where it's like, wow, it seems like all problems are graph structure problems, and it's a really powerful technology that should be applied to everything, like much like you mentioned earlier, and it becomes a problem in larger teams where some team members, may be very enthusiastic about graphs, other ones are not so much. And if you aren't careful to really break down the problem into the pieces that are generally graph problems versus the ones that should be solved with technology that we've been using for decades and decades and understand very well, then that can cause frustration and make the move to production much harder than anticipated. Because there is an element to scaling graph technology that is inherently harder because of the connectedness of the data, and you need to be aware of those elements as you move into production from building an initial prototype. And so going back to the recommendation of really make sure that the piece that you're tackling with graph technology is generally a graph problem will make everything else after that, in particular moving to production, so much easier, because you can immediately show the value that graph technology is bringing to solving the problem, rather than getting lost in an endless debate of whether this could have been solved with 50 million other different technologies that have been have been used in production for much longer and are much more well known amongst your team or amongst your company or organization that you work in. And so that's one element that we see quite a bit, where the initial enthusiasm might lead you down a path where you kind of overcommit a little too much for graph technology. Or likewise, people who are new to graph technology will undercommit, and they will be much more hesitant to adopt the technology. And so really working with the team to understand the happy medium path, and trying things out, building initial prototypes, taking those to production, seeing how they prove out, and then moving on incrementally from there is what we've seen to work best with teams on their path from, hey, we have a graph structure problem and we think graph technology can really help us accelerate our time to market, can really help us accelerate our value delivery and value extraction from that data, to moving that into production and successfully operating it against real workloads and against real scaling concerns. So general recommendation is take it easy, identify the piece that you want to solve first, move incrementally, and then be aware of all the things that Denise mentioned, and specifically, look into how the use case you're looking at has been implemented before, because there's lots of examples out there. We try to go through one new examples for each section of the book, so we can cover a broad array of use cases. So look into those and see which ones are similar to the one that you're tackling, so you can kind of see where the pitfalls are and where you can learn from past endeavors.
And then as far as the specifics of the database technologies, I know that there are differences in terms of the actual underlying data structures, but also the query syntax that they support, where Cypher has been a contender for a while from Neo4j, and they recently created the GSQL standard, which is largely influenced by that language. And then there was the Gremlin syntax, which has been an open standard that a lot of open source projects have been orienting around. I'm wondering what your thoughts are on the different capabilities that the different syntaxes have, and your hopes for the sort of coalescing of syntax to help with making the overall graph database space easier to adopt and easier to deploy and interface with multiple different tools.
Yeah, that's an excellent question. And one of the fun things about graph is that it is still fairly new. Like, all the products are very new. The query languages that are being proposed are very new. And so part of the fun of being in the ecosystem is that you can kind of see all these different ideas emerging, and like you can see how they merge together and form new ideas out of it. Like the GSQL initiative that you mentioned is sort of a merging of Cypher with some like SQL like superimposed graph type syntax that Oracle developed, and how those ideas are coming together. And Gremlin is taking a very different approach, looking at graph problems from a traversal-centric perspective, rather than sort of the declarative nature that the set declarative nature that SQL brings to the table. And so that, I think, is also a really, really interesting idea to kind of instead of trying to anchor the query language in SQL, which arguably a lot of people are already familiar with, but it does anchor it in a sort of set and relational world, where by relation, I mean the mathematical sense of a relation as a tuple, which is not the most perfect abstraction for a graph in many ways. In some ways it works really well, but in others it does not so much. And so you can see there being some benefits to Gremlin, which uses a traversal-centric syntax that allows you to kind of map your walk on the graph in a syntax that is very intuitive and path-like. It has sort of a functional vibe to it. And so those are all different ideas, and I'm really curious to see how they emerge and evolve over time. I think they're, the standardization initiatives that are on the way are trying to give the industry and adopters some sense of security, and that their knowledge investment is paying off over time. And so I think that's very important. At the same time, I think it's also important to keep an open mind and look at the world and see how, as graph technologies emerge and evolve, to make sure that we come up with a language that can really harness the power of that in a way that is easy to use for people, right? Like that's really the critical spot you need to hit with a query language. Is if you look at SQL and some of the earlier proposals that ultimately led to SQL, it was really about how can we harness the power of the relational algebra in a way that makes it easy for people to express, so that the database system can do the bulk of the work. And so we need to arrive at something similar for graph. And I personally don't think we're quite there yet. I don't think we have nailed this part, where we're still kind of putting together historical pieces with some of the stuff that we know, but it is still too hard at this stage, for instance, to build custom network flow algorithms in a declarative manner, to do simple and complex pathfinding type queries. Like all of that still requires a ton of syntactic gymnastics that make it somewhat awkward. So I think my opinion is we will see, like in 10 years from now, the world is going to look very, very different in that realm. And I'm really excited to see all the innovation that is happening, and excited to contribute to it and keep the conversation going, because I think that is really going to be the crux of it. How do we get people to be able to harness this tremendous power that is in a graph, right? Like when you think of like millions of interconnected pieces of data, and I want to ask a simple question like, how is person X related to person Y? Through the various types of paths that could exist in a social network, for instance, how can you give someone a query language that allows them to succinctly express their sense of what makes a path valuable, so that the database system can then do the heavy lifting of doing efficient path finding against optimized internal data structures that make this an efficient query to run without having to manually tune internal data structures, right? And we're not at that point yet. And we need to get to that point before graph technology can be widely adopted. But people who do not and should not need to care about internal data structure tuning and leave that up to the database level. So that's kind of the bar that I'm holding. And I don't see that we have met that bar yet. So I look at everything that's going on as sort of steps towards that goal. But I think that there's still a lot more to come in this arena. And I think that's going to be incredibly exciting.
And then looking beyond the database layer, what are some of the other components of the overall data stack and data lifecycle that either currently do or will eventually need to be able to work with and understand graphs natively?
Yeah, great question, Matthias. You might have more on that one, but I can start with what I think. So for tooling to kind of complete the ecosystem, I see, again, more from the practitioner and data science, data engineering perspective, I see two tools that really are needed. First, we really need a uniform layer for graph visualization, so that you have an easy way to manage and understand the structure of the data, but then seamlessly also communicate visually about the schema of your database, because because at the end of the day, your data schema, your graph database schema essentially functions as your map as you're attempting to process information in your graph database. So having a unified system that both visualizes your data and your schema is going to be something that I really hope to see emerge, because it's a critical piece in the stack as new technologists are picking up graphs. And the second piece I see, and this is definitely coming more from my perspective as a data scientist and a data engineer, having a notebook-like environment that more part of the global ecosystem for sharing notebooks, more like Jupyter or Zeppelin, having something that is more online so that technologists can share their graph work in this storytelling or developer driven notebook experience is going to be really critical for helping to share and communicate what almost everyone finds to be very fun and very exciting when they run their first traversals or they experience how to start to use graph data. That notebook-like experience gives them a communication point. And I believe that both of those tools uniformly across the entire graph ecosystem are really missing, so that we have more seamless enablement and communication about fun problems to solve with graph technology.
Yeah, I totally second Denise's point on graph visualization. There's a lot we need to do on the usability side of graph technology. I spoke to the query language earlier, which I think is one really critical component there, because that's really the interface at the end of the day. But we need to support that with tooling that allows you to understand what you're actually querying and how that query gets interpreted and run. And that's much harder to think about in the graph world, right? Like in the relational world, you can, you have the table as the abstraction, and that's a really nice abstraction because it's nicely two-dimensional and you can put it on a screen. And most of us are very familiar with navigating tables, columns, and rows, and we can kind of reason about that, and we can, reason about how the rows get filtered down if you put a where clause on some columns. Those are fairly intuitive things to reason about. Now with graph, if you even have a simple graph with like 1,000 vertices and 10,000 edges, like that already gets very overwhelming. And if you just put it on a screen, it looks like a spaghetti ball. That is this hard to penetrate. And so there's more work needed in terms of giving users enough visibility into the graph and the connectedness without overwhelming them, that we haven't quite figured out yet. There's a lot of really cool work happening there. And particularly, we have technology now that can visualize massive graphs, but there is sort of an inherent limitation to what our visual cortex can absorb and what we can reasonably make sense of. And we need to do a better job of really filtering it down and giving sort of the dynamic nature of the graph and the multidimensionality the right level of visual representation so people can make intuitive sense of it, which is really critical. On the other hand, I think another component is that graphs in many cases are emergent data structures. And what I mean by that is if I were to, let's say, send a text message to Denise, right? That's an interesting data point, right? Like Matthias sent a message to Denise on, this day at this time, and the message content was this long. Where it gets much more interesting is when you take all the messages together and you arrive at the global communication network. And now you're talking about a massively interesting data set that emerges from these individual events or individual data points. And so we need better infrastructure technology to really allow people to harness all these events and all this data that comes in and then build an emergent graph over time without having to do quite so much heavy lifting up front. Like right now, it is very laborious to plug the different streams and static and dynamic data sources together and build a graph from it. There's, parts of it are entity resolution related where you need to say, well, this phone number is the same as this phone number, or like those are the same individual and things like that. And all of that right now is still very manual, very laborious, and it delays graph projects quite significantly and oftentimes puts kind of a nail in their coffin because it takes you so long to get to that emergent graph that by the time you get there, people have already given up on the project. And so since there are so many common elements there, I think we can do a better job of building an ecosystem of tools around that to really help you build emergent graphs. And then on the downstream side, to make it easier to store such graph, to export them, to put them into data warehouses and on all these other like analytic tools that people are already familiar with. So basically making projections out of the graph that can serve other downstream systems that we're familiar with and comfortable with, so that there's less of that plumbing that we need to do to fit graph technology into an existing data infrastructure, which for most of us exists, right? Like there is, like the executives use a certain suite of BI tools to file their daily reports, right? So you need to make sure that the data goes there some way. Otherwise, it won't exist from their perspective. And that, again, needs to be something that becomes more automated and not a headache. It just is one of the things, and you have a tool that does that simply. So basically on the inside, on the sort of getting data in, building an emergent graph, then having the right tools, visualizations, notebooks, and other types of user interfaces that we have yet to build for this relatively new, not new in the sense of having been invented recently, but new in the sense of becoming popular as a data structure, this graph data structure. We do need new usability tools to work with it. And then on the downstream side, make it easy to project out of the graph to serve other systems and other use cases that rely on that data.
And as you look at the current trends in the overall industry of the technologies and the use cases for graph databases and applications built around graph structures, what are some of the overall trends and developments or just general improvements that you're seeing that you're most excited about and that you're keeping a close eye on?
Good question. On all the elements that we talked about previously, I'm really, really keenly interested to see how the query language conversation discussion is going to evolve, and how we are able to better connect with and pull users into the ecosystem. So for instance, we talked about Gremlin, we talked about Cypher, we talked about GSQL, but then there was kind of like out of left field came GraphQL, and it became an incredibly popular sort of API protocol in the JavaScript ecosystem. And it has it is called GraphQL because it looks at API consumption from a graph data perspective. And it has become wildly popular, much more popular in terms of if you look at raw numbers of developers using it than any graph technology that's on the market today. And so it's, I expect those things to keep happening, and they will all kind of influence each other to evolve towards this ultimate goal of a really user-friendly but powerful graph query language. And so that's one area that I'm really keenly interested in. And it's really interesting to see how even in areas that you think are completely unrelated to some extent, right? Like the whole problem of how does a mobile device consume data from a backend service, which is where GraphQL came from at Facebook, how that now is influencing the graph technology landscape quite heavily. And I expect that will continue to happen as graph structured data will become more and more valuable and more important. On the other hand, we talked about graph visualization. There's a lot of really good work happening there on both using GPU accelerated graph visualization so you can visualize larger graphs, but also being able to cluster the data in certain ways so you can kind of zoom in and out of a graph like you can with Google Maps, sort of, right? Like imagine you could only see the world like at the level of like street detail, like it would be very overwhelming. And so we can zoom in and out. And something similar we should be able to do with graph data, but we haven't quite figured out yet how to like semantically group things in the right way. So there's a lot of really good stuff happening there using modularity optimization. And then in terms of data structures and actual like query engines, there is, one of the fundamental realities is that our computer architecture, like the von Neumann architecture around which all of our computers are built, ignoring quantum computers for a second here, they all have an essentially linear memory, right? Like all of our memory is being addressed linearly, which is great for, continuous blocks of data. And this is why it's so fast to read, let's say, a movie off your disk, because you can sequentially read it off. And that is an incredibly fast operation. Jumping, from one page on your disk to another page is very slow. And so that tends to be the case with graph data, which is higher dimensional and in fact can be infinitely dimensional. So one of the really interesting questions is, how do you take graph data, which can be infinitely dimensional, and map it onto one-dimensional memory in such a way that you can minimize sort of jumping or seeking across disk or your SSD and pulling various pages into memory, and rather have continuous blocks that are co-accessed together, which is still very much an open problem. There's lots of really interesting research in graph partitioning, and there's interesting like partitioners elements to it. So how can you, like, as a partitioner, influence the schema in such a way that you get better locality on disk? How can we build better index structures so we can index graph data in a way that allows for faster retrieval of highly complex operations like pathfinding, for instance? So all of those areas are still very much work in progress, and I'm really keenly interested in seeing how they evolve and trying to keep tabs on the research that's happening, the technologies that are being built, and then stuff that comes out of left field like GraphQL did to some extent and tends to influence the space a lot.
Yeah. And Matthias, when I was listening to the question and then hearing your first answer, I could not be more aligned with your general first two recommendations. Right off the riff, number one, watching what happens with graph query languages is completely agree with you on that. Number two, though, with graph visualization, I would kind of go in a different direction with it, though. I think there's a need for better, I guess, more of a better developer experience from a visual perspective for understanding your schema, but then also just more localized traversals instead of global structures, which the nuance and the difference between how you and I see it really just is whether or not you're trying to visual very large segments of your graph or you're just trying to get confirmation about locally where you are. And I think the latter of that is where I have seen the industry pulling us more towards developing a better tool for the developer experience. Like there's just the initial initial perspective. And then lastly, as I was listening to your comments about how we better represent graph structures on disk and the different paging requirements, that was just reminding me of the emergence of neuromorphic computing that's happening, where people are starting to essentially create chips that are trained structures of neural networks for essentially solving that problem for one very specific application of machine learning and deep learning, namely neural nets. But I think that the advancements there in neuromorphic computing and how they are creating hardware for that acceleration could have a very interesting influence on how we approach storage of graph structures in the future. So interesting space to watch.
For anybody who wants to dig deeper into this problem domain or learn more about the overall space and applications of graph data and graph algorithms, what are some of the resources that you recommend?
That's great question. I'm always going to come from the perspective of get your hands on it and try something. I love to keep writing code or working on things until it's not working or you break something. So from that perspective, I have two recommendations. The first of which is, if you're just getting started, there are a ton of data sets on Kaggle where you can get your hands on graph structured data and see how people have solved graph problems like link prediction. So I recommend going there for Kaggle. If you want to go a little bit deeper, the SNAP, or Stanford Network Analytics Project, has both a synthetic graph generator in addition to a whole suite of graph data sets, some of which we use in our book. And then if you do want to get into using graph databases alongside our book, we have an entire technology stack of playing with data and these graph traversals for solving the most common problems. There's a really, really cool get started developer experience that we have them deployed in. It's called DataStax Desktop, and it has, just kind of gets everything ready for you so you can just get started with where exactly we have everything set up in the book. So if you want a vendor specific example, I would go to DataStax Desktop for just kind of exploring that getting started experience with the examples that we have in our book.
Are there any other aspects of graph technologies or applications of graph data that we didn't discuss that you'd like to cover before we close out the show?
No, I think we talked about most of the important elements. I'll bring it back to really, I think it is a really fascinating way to look at the world through the lens of graph structured data. And so for anybody who is listening and who finds this whole area somewhat interesting, I definitely second what Denise said about try it out, play around with it. And I would also recommend folks to sort of play with this notion of graph thinking and try to look at their problems that they're currently solving from hey, how would I solve this with graph? And what would it look like if I looked at this problem from the angle of a graph problem and applied graph thinking to it? Not necessarily because you're then going to go and do exactly that, but just kind of to train your brain a little bit to think in those ways. And you'll see how it really opens up your aperture for problem solving in a really fun and interesting way. And so that kind of, like talking about the technologies, I think the technologies are important, but I also think that the technologies are going to be very different 10 years from now, and they'll hopefully have evolved tremendously since then. But the one thing that I think is going to be the same is that you still, in order to use them effectively, you still need to be able to think in your brain in terms of graphs and apply graph thinking. And so learning that, I think, is a skill that will be useful for years and years, if not decades to come. And I encourage anybody who is interested in this to try this out and play around with this.
All right. Well, for anybody who wants to follow along with the work that you're doing or get in touch, I'll have you each add your preferred contact information to the show notes. And as a final question, I would just like to get your perspective on what you see as being the biggest gap in the tooling or technology that's available for data management today. Denise, if you want to go first.
Yeah, that's a great question to close with. And I'm sure you've kind of picked up on the theme throughout this podcast. I think that the biggest gap single-handedly is an easy to use graph query language. I think both Matthias and I are really looking forward to seeing the innovation coming from that space and on that topic. And to the points that we've made earlier, I think we're going to see innovation primarily in terms of ease of use, but then also trying to bridge the gap between relational algebra thinking, which was primarily SQL and relational databases, but then also bridging over to why people love graph data structures, and that's mainly from the graph theory perspective. So I'm really looking forward to seeing where we start closing the gap in graph query languages.
Yeah, 100% agree. It's all about usability. Like the technology is powerful. Graph thinking allows you to solve problems in a novel way. The big gap is making it easy for people to do so in a way that does not require you to have years and years of practical experience, but rather, get up and running quickly and solve problems in a matter of hours very effectively. And we're not there yet. And I think, understandably so, because it's still very, very, very new technology in very early days. But that will be the big item for us to figure out is how do we make this easy to use?
All right. Well, thank you both very much for taking the time today to join me and share your experience of working in this problem domain. As we've said, it's definitely something that is increasingly relevant and necessary for the types of data problems that we're being faced with. So I appreciate all of the time and effort that you've put into your work in the field and your work on this book. So thank you again for that. And I hope you enjoy the rest of your day.
Yeah. Thank you so much for having us. This was a real honor and pleasure to get to be on this. Thank you.
Yeah. Thank you so much. Have a good day.
Bye. Thank you for listening. Don't forget to check out our other show, podcast.init, at pythonpodcast.com to learn about the Python language, its community, and the innovative ways it is being used. And visit the site at dataengineeringpodcast.com to subscribe to the show, sign up for the mailing list, and read the show notes. If you've learned something or tried out a project from the show, then tell us about it. Email hosts at dataengineeringpodcast.com with your story. And to help other people find the show, please leave a review on iTunes and tell your friends and coworkers.